All right. So yeah, just quick about me. Been at Demandbase 4 years, focusing mostly on data platforms, and that's really been my career at software as a service companies. And I led Demandbase's migration to StarRocks here at Demandbase. So what is Demandbase? We're a leading business-to-business account-based go-to-market platform. We basically integrate all of your sales and marketing and ads data together in a single platform from all the different locations that you have this information, so that you can make the most of your sales and marketing budget by reaching out to the right people at the right companies at the right time. To power this platform, analytics is incredibly important. We provide this very powerful and very flexible system for our customers to analyze and explore all of this data that they're bringing into our platform, as well as the data that we're bringing to the table as well. This means that customers can highly customize their reports, they can bring in custom fields, and they can have complex rules for how they're going to filter and sort their data. And so we have a lot of configuration, a lot of configurability, a lot of differences between our customers, both in what they're trying to do, their data shape and size. And this brings a lot of challenges. Supporting live analysis means the queries need to be fast, and we need to be able to support a reasonable number of concurrent queries. In addition, because we have all this integration data we're bringing in from all different platforms, we have a heavy use of JSON blobs for data. This data can be, various formats, structures. It can be different from every customer, and then our customers can bring in their own custom fields into our system. And our big move onto ClickHouse was our original implementation of solving these problems at scale. But we had a lot of problems with our denormalization that was necessary for ClickHouse. And so the question becomes, why are we denormalizing? Can we not denormalize? So let's start with why are we denormalizing data, right? It's like reading data from a single table is usually faster. We'll get back to the usually later. Joins are computationally expensive. The repetition of data you get from denormalization is often considered an acceptable trade-off due to the low cost of storage. Disk is cheap. But denormalization is done not because we want to do it, but because we have to do it in order to meet the requirements of our companies and our customers. But there's a lot of costs, right? That read performance comes at the cost of write performance. You still need to join all your data together, but now it's done at write time as a whole global predicateless join of all the data. Changes to the underlying data set force recomputations of that denormalized data. And those costs increase if you need to replace entire partitions or the whole table because you're doing, mutations of data, especially. And then you have the problem of stale data when you denormalize. Your data is coming from multiple sources that comes into that denormalized view, and those updates to the underlying data, they'll be stale in your denormalized data until you update. That means that you can have a lot of uncertainty around when data is going to appear, and the order of which data will appear. Table one might be updated in time to get into the next view of data, but table two may not, and so you have unexpected changes between your data that are difficult to explain. And then that data amplification that's usually considered acceptable can spiral out of control. When you denormalize one-to-many relationships, you create large numbers of copies of data. Take this example of a simple order and customer table. Your order table might have just a few small columns, mostly numeric, but you'd have a huge number of rows, lots and lots of orders. But a customer table, you might not have a lot of customers, maybe tens or hundreds, but it might contain a lot of data in every row, big strings, complicated information. And so you end up replicating that large data time and time again, and that causes problems with the amount of storage you're using. And then with all of that, sometimes all this work you've done to make queries better and perform better actually makes things slower because of the denormalization. That deduplication can mean that you're reading way more data than you would have in a normalized fashion. And then filters on that denormalized data, well, now you need to run that on every single row. Imagine something like looking at, a substring of an address of a customer. In denormalized data, you're going to have to read every single row and do that filter. Whereas if you had normalized data, you'd only have a few of those to look through, and then you would join that data with that bigger table of orders. And so we faced a lot of problems with denormalization, especially with ClickHouse and making this all work. We had 40 plus ClickHouse clusters at scale, and loading became this massive bottleneck that we constantly fought against. We were constantly working on trying to make it so that we could meet this requirement of updating our daily just once per day. Each one of our clusters had 2 read nodes and then 1 dedicated write node whose sole job was to pull in data into the ClickHouse format and pass that on to the read nodes. And even that was not enough. We ended up building a custom process that created the ClickHouse data files outside of ClickHouse and then passed them in to the ClickHouse read nodes. And then we estimated our storage costs were 10 times more than what it would have been if we had normalized our data. And so we ended up spending more data on disk than we did in compute for our ClickHouse clusters. And this was really problematic. In addition, we did all this work to denormalize our data, but we were still doing joins. We had frequent joins to these list membership tables. So, a list ID and then a list member ID. We needed to filter on that data all the time, but we couldn't put that into denormalized data. So we had to frequently join that data together. And then for some rapidly updating tables, we also had to make external connections to Postgres. So we were reading data from Postgres during the query and then having to join that data into the data from ClickHouse. And so our query performance still just wasn't meeting the needs that we had for the business in a lot of cases. And why were we having these challenges? Well, we're loading a number of tables into ClickHouse, but we have 3 main kind of data objects that really tell the story. The first is accounts. You can think of those as basically companies, but sometimes companies can be multiple accounts that you're selling into. So we have accounts, people that work at those companies, and then we have events. Those could be clicking on a link, visiting a website, downloading a white paper, all events happening by people in your platform. And those account objects are very large. They're 20 times larger than the normal events data. But by number of records, the events are massive. They dwarf all the other tables combined. And so we were denormalizing these 3 underlying data sets together into ClickHouse. And that meant we were denormalizing onto the events all of these accounts, these large objects. And so we were basically duplicating them 100 times over, our largest objects, into our denormalized view. And that was causing us significant problems. So we looked at StarRocks to get away from this pattern that was causing us so many problems and looking at normalization of our data. And so let's talk about how StarRocks makes normalization possible at the scale of analytics. First, it has a lot of strategies around making distributed joins possible. Broadcast joins when one tie of the join is small, shuffle joins in other cases, and then because it's a distributed system, you can use the resources of all your nodes, not just a single node. So on a certain level, you can also brute force your way through making the joins acceptable in terms of performance. And then there's lots of optimization, especially in the cost-based optimizer for intelligent query planning within StarRocks, which is a really key feature of the system. You can conduct join reordering to make it so that at runtime, you're doing these joins in the best order that's going to give you the fastest results. Runtime filtering of the large side of a join to improve the performance as well, and just a host of other optimizations that StarRocks implements. I find the runtime filtering of joins a really important and powerful tool. In a normal case, you might be scanning 2 tables, one large, one small, and then in a distributed join, you need to shuffle all of that data by the hash of the join keys, and then complete your hash join. But with StarRocks, what it can do is take those keys, those join keys from the small table, and exchange that small amount of data to the nodes where the scan of the larger table is happening, and at runtime filter that data. So now you're filtering down the amount of data that's actually involved in that shuffle, which is usually one of the most expensive parts of the join, greatly improving performance, removing a lot of your network traffic, and getting you the kinds of results that you desire. Another ability of StarRocks that we made heavy use of was Colocation Joins. So StarRocks allows you to define multiple tables with the same distribution strategy on the join keys that you're going to be using. So for example, we might define the distribution based on an account ID, which would be the ID column in the account table, and then in the person table, it would be the external account ID. And so our data will be distributed by that column for both tables. And that means that in StarRocks, all of the data for that given ID exists on one same physical node, which means that now what was a distributed node becomes a local, distributed join becomes a local join. And so now you're greatly reducing your network traffic and the memory required in your joins, because now you're doing it locally. You do need to be careful with this ability. If you're using colocation and you have problematic skew problems, this can actually result in lower performance. For example, we had this special account foreign key ID, account ID 0, which is basically an unknown person, someone we don't know who the account is. And this was often making up huge amounts of the data for a lot of our customers. So not locating meant that we had higher network traffic and higher latency, but we were able to get around this problem by fixing our skew, by adding a kind of a synthetic key to make it so that we were now distributing over that special zero ID over more IDs, which removed the problem and got us back the performance we desired. So where are we heading now that we've gotten a level of normalization in place? Well, we're trying to continue to break down our tables into smaller and smaller pieces and further normalize our data. We have situations where we might have multiple integrations, which historically we jammed into one table. Now we can have those integrations be each getting their own tables and simply joining in the right data at runtime. We can take dimensions that we're loading and then metrics that we're calculating and do those in separate tables, allowing us to do those at different cadences and frequencies. And then we can give our engineering teams stronger ownership of their data by allowing them to have their own table where their data goes, allowing them to really control when their data is updated and decoupling it from when other data is updated. So hopefully you've seen there's a lot of abilities in StarRocks to move away from denormalization. We've certainly had a lot of success moving to normalization, but it can be a big shift and a big change to what you're doing. So how do you move away from denormalization? You already have a denormalized system. How do you move to normalization? So there's a couple things that we did at Demandbase to make this possible to migrate. The first was we created in StarRocks views that presented the data as if it was still in the denormalized schema. Under the hood in StarRocks, we had the normalized tables, but we were still querying it through that denormalized view. That greatly reduced the amount of effort required by our engineering teams to migrate their queries. They didn't have to rethink the way they were doing things. They really just had to translate the queries into the StarRocks syntax. And in most cases, we were able to just continue forward. That greatly reduced the amount of work that we needed to do. And now in the future, all of our queries can go at that normalized schema. And eventually we were able, we can get rid of that denormalized view and that can go away. And then even in that interim time period, we're still getting that benefit of the normalized tables, decoupling the cadence of their updates, even as people are going after that denormalized view. We used our existing denormalized data to load our normalized tables. So this meant we weren't doing a whole nother effort of work normalizing the data outside of StarRocks first. All of our data was first going into Iceberg tables in S3. And so we were able to continue using that denormalized data to feed ClickHouse during the migration. But we could also just reuse that data to load StarRocks by ignoring all of the columns that were denormalized into those tables and just get the columns that we needed for our normalized tables. This greatly reduced the scope of our migration and allowed us to focus really on one part. And then later on, now we can focus on normalizing the data upstream of our database. Another really important thing that we utilized based on the fact that we were creating this denormalized view was avoiding unnecessary joins by using StarRocks foreign keys. In this denormalized view, you might not always need columns from each of the tables involved in that view. You might be looking at events by account, and so you don't need any data from the person table. But if you're defining this view as a join between those three tables, well, all three tables are still going to be involved in that join. And that's where foreign keys in StarRocks come into play. They're not going to give you the same kind of enforcement that something like a foreign key would in something like Postgres or other relational databases. It's more of kind of a hint to the query optimizer to say, hey, I guarantee that there's a relationship between these tables that can possibly allow you to skip this table if you don't need any data from it when you're running the query and you're doing joins. You can just drop that table's joins from the entire query and greatly increase your performance. And then I should say the last thing is the secret weapon of StarRocks is the cost-based optimizer. The cost-based optimizer is always making your queries better and is always improving all the time. And it uses statistics of the tables in order to, order joins, optimize the query plan, try different approaches. And so StarRocks is determining the best way to run your query rather than running it as written. And this is incredibly helpful during a migration because you have queries already and you're trying to take them from one system that works in a different way to StarRocks. And even though you haven't written your queries in a way that's really designed to take use of the things that StarRocks brings and offers, in fact, we're hiding the fact that we're using normalized tables in our denormalized views. StarRocks can really kind of, for free, kind of optimize those queries for you. And I think in 95% of the cases, we really didn't have to make any changes to our queries to get good enough performance or even significantly better performance in StarRocks than we were before. With really no changes. We didn't have to, change the way we were running the query, restructure it to make it work in StarRocks, which was extremely helpful and really moved forward our migration. The cost-based optimizer is only as good as the quality of your table stats. Tables with skewed data between partitions can sometimes be a problem and throw off this cost-based optimizer. But we've worked with seller data and the StarRocks community. And the community continues to work on further optimizations of the cost-based optimizer to handle these problems and more. And really, we've seen every single time a new version of StarRocks is released, significant improvements in query performance with us having to do nothing at all. So hopefully you've seen that it's really possible, and there's easy ways to move yourself from a denormalized world into a normalized world and gain all of the benefits of normalization while still getting that performance that your business requires. And this is something that's really achievable with StarRocks. And it's been incredibly successful at Demandbase. It's improved our performance, latency, our costs have gone down significantly. And we're really just getting started in reimagining the way that we tackle data here at Demandbase to get the most out of it with all the power that StarRocks gives us. And with that, thank you very much. I'd like if there are any questions.
Nick, thank you so much. That was fantastic. You have been a enforcer. You timed this out to the minute. It was great. Left us plenty of time for Q&A, and the questions are coming in for sure. Let me ask, a couple of them came in through the chat and a couple through Q&A. So Sean asks, do we all hash the ACC ID to prevent the skew problem?
So the problem with our case where we had this account ID column that we were hashing it, but if you have one ID value that most are like a large amount of your data, hashing doesn't distribute it. So you're still stuck. If you have many keys, hashing really helps distribute things well. But when you have one key that sticks out and gives you terrible skew, you have to break that key down. There's many ways to do that. One of the ways that we did it was that we simply we designed our data so that we had a bunch of like negative IDs, like 100 negative IDs, and we just kind of randomly distributed all of the account ID equals 0 values across those. And that allowed us to get rid of that skew that was hurting our system.
Thank you so much for that. Anton Borisov, who not only is asking a question, making a comment, is presenting today and has a fantastic Medium article. If you haven't found it already, please read it. Always nice, by the way, to have a fellow presenter asking questions and attending your session. He says that resembles what we've done at Fresha for homepage analytics.
Yeah, I mean, that's exciting. And I think, I think you've already, if you've been, going to a lot of the sessions, you've already heard of several, and you'll probably hear several more similar scenarios where, people, thought that they had to denormalize their data. It was the only way we were ever going to do analytics. And StarRocks has really changed the game in that front.
Awesome. Zen Chao says, do you run sampled stats run or full data?
For a few of our tables, we've had to go with just sampling because of the size and some of the challenges with the data. Those, some of those challenges are things we're still working on now that we're, in a different environment where we have much more flexibility. But ideally, we would be running full statistics. But there's just a few cases where we're not able to.
Thank you very much. We have a question in from the Q&A. Can you talk about how you managed the migration process? How did you make sure everything was working on StarRocks before flipping the switch from ClickHouse?
Yeah, so we were running both in parallel. And again, because our source data was an iceberg, this was easy for us to be doing, just run both in parallel. And the application that was running queries, we created a mirror copy of it. And so every request was actually going to the real one that was handling traffic from ClickHouse and to our customers, and then a shadow one where it was hitting the StarRocks. And we were then just putting that data into basically Kafka, and then we were doing analytics on that data to figure out if the results were the same, comparing the performance, and making sure that our migration was going successfully. So we've had quite a few data migrations at Demandbase, and they've all been really challenging. And you lurch forward and try the new thing, and then you roll back because you found problems. And in this case, because we were able to do that parallel work, once we turned on StarRocks, we never went back. Everything just rolled forward, and we had a surprisingly smooth migration.
That's great. I think we may have time for one more question. It's a longer one. Kalyan says, do you have events with a common unique identifier spanning across a funnel of events, and you have to stitch multiple events for the same identifier? So he says, let's say the identifier is a session ID. If that's the case, how about we store the events in one big table implemented as primary key table in StarRocks, the primary key being the session ID. No column is populated by more than one producer. I now have all events for a session in a single row. Is this also your case? If yes, how do you evaluate the design pattern?
So that's a great way to do sessions. One of the challenges we have is actually a lot of our data isn't session data. It can be data that's being imported from one of tens of integrations, from like Salesforce to Marketo, or even just like uploaded from a CSV. Maybe they're signups you got at a booth at a conference. And so we really have a mishmash of types of events. And so we don't really have that ability to focus on just one type of like session where we could merge multiple rows together into a single session ID. But what you're describing is definitely the way that you would want to try to approach a session-based event stream.
Awesome. And we're at time. So thank you, Nick, again for joining us for this great Q&A also. Thank you for those questions from the audience. Don't forget to complete the evaluation question that's in the poll following the session. And our next sessions are starting right now. So we'll see you in the next one.
Thank you very much,